Far beyond Neptune, a pale world drifts through near total darkness, reflecting only a thin thread of sunlight back toward Earth. It looks like a simple moving dot in survey images, yet its size, its moon, and its distant orbit quietly reshape how the solar system is described. Tonight, this calm documentary follows Eris and the real science behind the discovery that changed the definition of a planet, from the patient work of sky surveys to the measurements that reveal a true world on the frontier. Before settling in, please like the video, subscribe to the channel, and let this slow journey beyond Neptune carry the night gently forward. Far beyond Neptune, the solar system becomes quiet in a particular way. The sun still rules the motion of everything, yet its warmth and brightness thin out until they feel more like a background condition than a daily presence. Out here, an object can take many years to shift noticeably against the starry backdrop, and the same sunlight that warms Earth to comfortable temperatures becomes a faint, distant glow. In this outer region, Eris travels on a long, stretched path, spending most of its time in cold darkness where the sun is only a brilliant star and where the landscape, if it could be seen closely, is shaped by ice, vacuum, and time. The solar system is often pictured as a set of neat rings, but its outer edge is not a clean line. Beyond Neptune, the sun's influence continues in a broad domain of small worlds, icy bodies, and leftover building material from the solar system's formation. These objects are remnants of a time when gas and dust around the young sun gathered into planets, moons, and smaller fragments. Many of the fragments never became part of a large planet. They remain in distant reservoirs where gravitational nudges slowly rearrange their paths. Eris belongs to this distant population, and its story begins in that cold setting rather than in a debate about definitions. Sunlight spreads outward as it travels. The same energy must cover ever larger spheres as distance increases. That means the intensity falls quickly. By the time sunlight reaches the region beyond Neptune, its ability to heat surfaces is greatly reduced. An icy world out there does not receive a steady bathing of warmth. It receives a weak illumination that is enough to cast shadows, but not enough to do much work on temperature. Surface heat leaks away into space, and the balance settles close to the freezing point of most gases, and far below the conditions that allow liquid water on the surface. Ice is not only water ice. Ice can also be nitrogen, methane, carbon monoxide, and other volatile materials that would be gases nearer the sun. In the outer solar system, these volatiles can freeze onto the ground and remain stable for long periods. The darkness is not complete. Starlight exists everywhere, and the sun is still bright compared with other stars. Yet the sun's disk appears smaller, and its energy is weaker. A distant world like Eris is not lit by a broad, warm day in the way Earth is. It experiences a thinner kind of daylight, with a colder colour of light and a much smaller energy input. The surface temperature depends on reflectivity and on distance, but the overall environment remains cold enough that most chemical activity is slow. Processes that happen quickly on Earth can take centuries in these conditions. Frost can remain undisturbed. Craters can persist. The surface becomes a record of impacts and of subtle seasonal changes rather than of rapid weather. Eris moves through this region on a path that carries it far from the sun for long spans of time. The path is not a simple circle. It is an elongated orbit, and it is also tilted relative to the main plane in which most planets travel. This means Eris does not simply circle in the same flat disk as Earth and Neptune. It rises above and below the plane, taking a high, slanted track. Over the course of its long year, the distance to the sun changes greatly. This changing distance produces changing sunlight and changing temperature, but the changes unfold very slowly. The seasons of Eris, in the broad sense of changes in solar heating, occur over intervals that stretch across generations. The outer solar system is also sparse. The distances between objects are large. Even in regions that contain many small bodies, the density in space is low. Collisions happen, but they are rare compared with a crowded early solar system. The objects are separated by vast spaces of near vacuum. This vacuum is not absolute emptiness, but it is thin enough that it provides little resistance to motion and little capacity for heat transfer. Without an atmosphere, a surface radiates heat directly to space. Without air, sound does not travel. The environment is quiet in a literal physical sense. If Eris has an atmosphere at all, it is expected to be thin and temporary, tied to the slow changes in temperature along its orbit. Most of the time, this surface behaves like exposed ice in vacuum. At this distance, the night sky is dense with stars. A world far from the sun sees the Milky Way as a bright band, and it sees constellations much as Earth does. Though the sun's position among the stars is different, the planets closer to the sun would still be present as bright points in the sky. But their apparent motion would be slow and subtle. The most important dynamical influence in this region is still the sun's gravity, but Neptune also plays a significant role. Neptune is the outermost giant planet, and its gravity shapes the architecture of the distant reservoirs. Some objects remain in relatively stable patterns that reflect resonances with Neptune, where orbital periods form simple ratios. Other objects have been scattered into stretched orbits by close gravitational interactions. The distant region is therefore a mixture of orderly patterns and long-term chaos, with objects slowly migrating through orbital space under the influence of gravity. Eris belongs to the category of distant worlds that are not confined to the simple belt-like picture. Its orbit is part of a population of bodies whose paths have been altered and elongated. The details of that population will come later. For now, it is enough to hold a calm sense of place. Eris is a world of the outer frontier, moving through cold, thin sunlight, far from the bright inner planets. It is not near a planet in the way a moon is. It is not passing close to the sun in the way a comet does for most of its existence. It is an object that spends most of its time in a deep outer zone, where any change is slow. This outer setting also frames the practical challenge of discovery. A distant world reflects only a tiny fraction of sunlight back toward Earth. Even if it is large and reflective, it appears as a faint point. The motion is slow because the orbit is large and the speed is modest in angular terms as seen from Earth. The object hides among countless background stars. Dust and gas in the Milky Way can add confusion in some directions, and the density of stars can make a faint object harder to separate. Therefore, the outer frontier is not only physically distant, it is observationally demanding. Finding a world like Eris requires patient surveying, repeated imaging, and careful comparison over time. The discovery that changes definitions does not begin with definitions. It begins with this far region where definitions are not visible. There is only a faint dot of light moving slowly through a star field. The meaning comes later, after orbit and size are constrained, and after the object is placed into the growing inventory of distant worlds. The first layer of the story is therefore a quiet physical one. Eris exists in the cold frontier beyond Neptune, where sunlight is weak, where ice dominates, where motion is slow, and where the solar system's leftover building blocks persist as a distant population. From this far stage, the inward path narrows to the neighborhood structure of that frontier, separating the relatively stable Kuiper Belt region from the more scattered populations that include highly elongated and tilted orbits like Eris's, and showing how the giant planets shape these distant reservoirs over long time. Beyond Neptune, the outer solar system is not one uniform belt. It is a set of overlapping populations, each with its own typical orbits and its own history of gravitational shaping. Two terms appear repeatedly in the science of this region. The Kuiper belt describes a broad zone of icy bodies that orbit beyond Neptune in comparatively stable paths. The scattered disk describes a population of bodies with more stretched and tilted orbits, shaped by stronger gravitational interactions, especially with Neptune. Eris belongs to this second category. Its orbit is a clue that it does not merely sit in place. It carries a history of scattering, long-term stability at great distance, and slow seasonal change driven by an extreme orbital shape. The Kuiper belt is often described as a reservoir of small icy worlds and remnants left over from planet formation. It occupies a region beyond Neptune where objects orbit the Sun with semi-major axes, a measure of orbit size, that are generally tens of astronomical units. The orbits of many Kuiper belt objects are not perfectly circular, but they tend to be less extreme than those of the scattered disk. Many also have inclinations that are modest compared with the most tilted distant bodies. In this belt-like population, the outer solar system looks, at first glance, like a distant echo of the main planetary plane. The belt is not a dense ring. The objects are separated by vast distances, but their orbits occupy a broadly similar region. Within the Kuiper belt, there are subgroups that reflect how Neptune's gravity organizes motion. Some objects are in resonance with Neptune. A resonance is a situation where orbital periods form a simple ratio, so that the object and Neptune return to similar geometric configurations repeatedly. Resonances can protect objects from close encounters with Neptune by ensuring that when their paths cross in distance, they do so at different times or at safe separations. Pluto is the most famous example of a resonant object, but it is not unique. Resonant Kuiper belt objects show that Neptune's gravity does not only scatter, it can also shepherd and stabilize. Another subgroup of the belt includes objects sometimes called classical Kuiper belt objects, which have relatively stable orbits that are not in the strongest resonances. Even within this group there is a spread. Some have relatively low inclinations and lower eccentricities, suggesting a calmer dynamical history. Others have higher inclinations and higher eccentricities, suggesting past stirring. The belt therefore contains both a colder, more orderly component and a hotter, more dynamically excited component, where hotter refers to orbital stirring rather than temperature. This variety hints at a past in which the giant planets shifted and the belt was disturbed, leaving behind a structured population. The scattered disk differs in a clear geometric way. Scattered disk objects have orbits that take them far beyond the main Kuiper belt region at their most distant points, while still bringing them relatively closer to Neptune at their nearest points, at least in a historical sense of orbital shaping. Their eccentricities are often high, meaning their distance from the Sun changes greatly over one orbit. Their inclinations can be high as well, meaning the orbit is tilted strongly relative to the plane in which most planets move. These features suggest a history of close gravitational interactions. Neptune is the main agent. An object that passes near Neptune can have its orbit changed. It can gain energy and move to a larger orbit, and it can also have its orbit tilted. A series of such interactions can populate the scattered disk. Scattering is not a single moment for all objects. In the early solar system, the giant planets likely interacted with a massive disk of planetesimals, smaller bodies that were building blocks of planets. As the planets migrated, their resonances swept through the disk, capturing some objects and scattering others. Neptune's outward movement, in particular, can scatter bodies into more distant orbits. The present scattered disk can therefore be viewed as a fossil of that dynamical evolution. It contains bodies that were thrown outward but not ejected entirely. They remain bound to the Sun, returning on long paths that keep them far away for most of their orbital periods. Eris's orbit fits this picture. It is strongly elongated and significantly tilted. That means Eris experiences extreme changes in distance from the Sun over its long year, and it also spends much of its time well above or below the planetary plane. The orbit suggests that Eris's path is not simply the result of gentle formation in a quiet belt. It reflects a past in which strong gravitational interactions shaped the trajectory. At the same time, the orbit is stable over long time in the sense that Eris remains bound and does not repeatedly return to close planetary encounters that would eject it. Its present path is a settled outcome of earlier chaos, a long-term stable lane in orbital space. The difference between the Kuiper belt and the scattered disk also matters for discovery. An object in a more circular belt orbit stays at roughly similar distance from the Sun, so its brightness varies less over time. An object in a scattered orbit can be much brighter when it's closer to the Sun and much fainter when it is far away. Because brightness is central to detection, scattered disk objects can be discovered preferentially when they are closer, even if they spend most of their time farther away. This creates an observational bias. Surveys are more likely to find such objects near perihelion, the closer part of their orbit, because they are brighter there. When an object like Eris is discovered, it may be in the part of its orbit where it is detectable, even though that part is a minority of its full orbital path. The scattered disk is also linked to an even more distant concept: detached objects. Bodies whose perihelion is far enough from Neptune that present-day scattering by Neptune is weak. Some of these objects may have been influenced by mechanisms beyond simple Neptune encounters, such as resonance interactions during planetary migration, or perturbations over long time from passing stars or the galaxy's tidal field. The boundaries between these categories can be subtle, and classification can depend on how an orbit is defined and measured. The calm and practical point is that the outer solar system contains more than one population. It contains objects whose orbits remain relatively close to the belt region, and objects whose orbits stretch far beyond it. The Kuiper belt and scattered disk together change the meaning of the word planet in the story of Eris, but that shift belongs later. In this region, the focus remains on orbital architecture and what it implies about origin and history. Eris is one of the largest known bodies in the scattered disk, and its existence demonstrates that the outer frontier contains worlds that are not merely small debris. It contains large, spherical bodies with moons and complex surfaces, moving on orbits shaped by Neptune's long gravitational reach. This architecture also implies a certain kind of solar system boundary. Neptune is not the end of the solar system structure. It is a gateway. Beyond it lie populations that are sculpted by Neptune's gravity. Resonances create islands of stability. Encounters create scattered trajectories. Migration in the early solar system leaves behind patterns that can still be read today. Eris is a signature of that pattern, a large body on an extreme orbit, preserved as part of the scattered population. From this map of populations, the inward path now moves from orbital categories to the human method of finding such distant objects. The next region focuses on survey telescopes and repeated imaging, showing how a faint point is separated from background stars by patient comparison across nights, months, and years. Finding a distant world like Eris begins with a simple visual fact. against the background of stars, a body in the solar system moves. The stars are so far away that their positions do not change noticeably from night to night in ordinary images. A distant object beyond Neptune, however, shifts slightly. The shift is small because the orbit is large and because the object is far away, but it is real. Survey astronomy uses this small shift as a signal. It takes wide-field images of the sky, repeats them, and searches for points of light that move in a consistent way. The method is patient and systematic, and it becomes more powerful as telescopes, detectors, and computer analysis improve. Wide-field surveys are designed to cover large areas of sky efficiently. A large camera at the focus of a telescope can record many stars and galaxies at once. The survey takes an image, then another image of the same region later, and compares them. The time gap can be hours, days, or longer, depending on the target population. Near-Earth asteroids move quickly and can be detected over minutes. Trans-Neptunian objects, the general term for bodies beyond Neptune, move slowly. Their motion may be visible over a few hours as a tiny displacement, and it becomes clearer over days and weeks. The survey cadence is therefore tuned to the expected speed. For the outer solar system, this search looks for slow movers that shift subtly relative to the star background. The motion seen from Earth is a combination of the object's own orbital motion and Earth's motion around the Sun. Earth's movement creates a parallax effect, an apparent shift in position against the background as the observing point changes. For nearby objects, this shift is large. For distant objects, it is smaller but still present. In practice, the apparent motion of a trans-Neptunian object is influenced strongly by Earth's motion because Earth moves relatively quickly compared with the object. This means that the object's apparent path on the sky can reflect the geometry of the observing season. The object can appear to move in a gentle arc over weeks and months as Earth's position changes. Survey methods incorporate this by focusing on regions of sky where trans-Neptunian objects are more likely to be found, such as near the ecliptic, the plane of Earth's orbit projected onto the sky, while also recognizing that high-inclination objects can appear well off that plane. The practical detection process often begins with a set of images taken on the same night. Analysts search for points that shift between images while keeping a consistent brightness and shape. The image shape matters because many background objects, such as distant galaxies, appear slightly extended rather than point-like. Stars appear as points blurred by the atmosphere and telescope optics. A trans-Neptunian object also appears as a point, so it can be confused with stars unless motion is detected. By comparing images, a moving point can be distinguished. Software can blink images, rapidly alternating them, so a moving object appears to jump while stars remain fixed. Modern surveys also use automated algorithms that detect candidate motions and score them for consistency. False positives are common. A cosmic ray hitting a detector can produce a bright pixel that appears in one image but not another. A detector defect can mimic a faint object. A variable star can change brightness and look different between images even though it does not move. Atmospheric conditions can change seeing, altering the apparent shapes of stars. Therefore, survey pipelines include filtering steps to reject artifacts. Candidates are then confirmed by additional observations. A real trans-Neptunian object should continue to move in a predictable direction and speed. Confirmation over multiple nights is especially valuable because it reduces the chance that a random artifact is mistaken for a real body. Once a moving object is identified, the next step is orbit estimation. With only a short arc of observations, the orbit is uncertain. Many different orbits can fit a few positions over a few days. Yet the observations provide constraints. The apparent rate of motion, the direction of motion, and the curvature of the path all carry information about distance and orbit size. A distant object moves more slowly and shows different parallax behavior than a closer one. Initial orbit estimates can therefore classify the object as likely beyond Neptune and can predict where it will appear in the sky on subsequent nights. Follow-up observations then refine the orbit. The discovery of Eris is closely tied to the power of these survey methods and to the willingness to revisit and reanalyze data. Large surveys generate enormous data sets. Not every faint moving object is detected immediately, especially if it lies in a crowded field or if the observing cadence is not optimal for its motion. As software improves and as analysts gain experience, older images can be searched again. In some cases, objects are found in archival data that were not recognized at the time. The ability to link observations across time, connecting a moving point seen on one date with a moving point seen months or years later, is a major step. It transforms a faint dot into a tracked object with an orbit. Brightness also plays a role. A large object far away can still appear brighter than smaller objects at similar distance, especially if it has a reflective surface. Brightness alone does not prove size, because reflectivity varies. A small icy object with high reflectivity can appear similar in brightness to a larger, darker object. Yet an unusually bright trans-Neptunian object is a compelling candidate for being large. This is part of why Eris stands out. It is bright enough among distant objects to attract attention once its motion identifies it as far away. The combination of significant brightness and slow motion suggests a large body at great distance, a combination that deserves careful follow-up. The sky region searched matters because the outer solar system populations are not uniformly distributed. Many objects are found near the ecliptic because that is where most orbits cluster. Yet Eris has a high inclination orbit, meaning it can be found far from the ecliptic. Surveys that cover only a narrow band around the ecliptic can miss such objects. Broader surveys that extend to higher ecliptic latitudes increase the chance of finding high inclination bodies. This is one reason why the inventory of the outer solar system changes with improved survey coverage. Objects like Eris demonstrate that the frontier is not confined to the thin plane of the planets. Observations also depend on timing. An object's visibility changes with Earth's orbit because the object is best observed when it is opposite the Sun in the sky. A configuration called opposition. Near opposition, the object is visible all night, and its apparent motion pattern is favourable for detection. Surveys often plan to observe near opposition for outer solar system searches. Over successive oppositions, the object's motion can be tracked, and orbit estimates can be refined. This long-term tracking is essential for an object like Eris because its orbital period is measured in centuries. A few months of data are only a tiny fraction of its orbit. Yet the geometry of the observations allows a good orbit estimate if the arc is long enough and if the measurements are precise. The method therefore turns stillness into motion. It uses repeated imaging, careful comparison, and follow-up tracking. It converts a faint dot into an orbit, and then into a world with a defined place in the solar system. This is the observational foundation that allows later questions about size, mass, and classification. Without this patient survey work, the debate that Eris triggers would not have a subject. From this method layer, the inward path now moves to the moment Eris stands out within survey data, focusing on how it is recognized as unusually significant among trans-Neptunian discoveries, and how its brightness and motion hint at a large object beyond Pluto. In a wide-field survey image, Eris does not announce itself as a world. It appears as a faint point among many other faint points. each one fixed in place from the perspective of a single exposure. The first step toward discovery is not a single dramatic observation. It is the quiet realization that one point is not fixed. When images of the same patch of sky are compared, a subtle shift becomes visible, consistent across frames and consistent with the slow motion expected of a distant solar system body. In this way, the data that first contains Eris carries its significance silently until careful analysis extracts it. Survey data is often gathered in large quantities, with many nights of images taken across wide swathes of sky. The goal is to find moving objects, yet the number of moving objects at great distance is small compared with the number of background sources. The more distant the object, the slower the apparent motion, and the fainter the reflected light, which means the signal sits closer to the detection limit. A candidate can be missed in an early search if the motion is too slow to stand out in the chosen time gap. If the object is near the edge of the detector where image quality is poorer, or if the field is crowded and the object blends with nearby stars. This is why archival images can later become a second discovery site. What was once unrecognized becomes visible when the search method changes. Reanalysis becomes possible because the star background provides a stable reference frame. Stars in a given patch of sky remain in the same relative configuration from night to night, with only tiny shifts that are irrelevant at the scale of typical survey imaging. When software aligns images to the star field, any solar system object will shift relative to that fixed pattern. The shift can be measured precisely if the object is detected in multiple frames. In practice, the analysis looks for a set of positions that can be linked together by a plausible motion model. At great distance, the expected motion is small and smooth. The candidate does not streak across the frame. It drifts. In the case of Eris, the first clue is an object that appears brighter than many other trans-Neptunian candidates at a similar apparent motion rate. Brightness alone does not prove size, because reflectivity varies, but unusual brightness at a slow motion rate is a useful combination. A nearer object can also appear bright, yet it would tend to move faster across the sky, and its parallax signature would differ. A very distant object moves slowly, and when it's also relatively bright, it suggests either a large body, a highly reflective surface, or both. This is the kind of evidence that justifies careful follow-up. Follow-up begins by predicting where the object should appear in the next set of images. Even with a short observational arc, the direction and approximate rate of motion provide a workable prediction. If the object is found again where it is expected, the case strengthens. If it is found across multiple nights and then across longer time intervals, the orbit estimate becomes more constrained. Once an orbit estimate exists, analysts can search older images for the object's past positions. This is where earlier data becomes important. A faint dot in an image from a prior year may match the predicted position. When it does, the observational arc extends backward and the orbit becomes more precise. Each recovered point reduces uncertainty and makes the object easier to track in the future. The data that first contains Eris therefore includes both fresh detections and recovered detections. The practical effect is that the object's motion becomes a continuous thread across time. Instead of being a single faint point, Eris becomes a sequence of points. That sequence is the beginning of a world. The orbit derived from it reveals that the object lies beyond Neptune and that it follows a highly elongated path. The orbit also places the object within the broader population of distant bodies that are not confined to a simple belt. This classification in orbital space is one of the first scientific results of discovery, and it comes directly from the pattern of positions in images. Brightness and color measurements in the discovery data provide additional clues. The light reflected by a distant icy object can be reddened by surface composition and by space weathering, and it can also be reddened by the viewing geometry through Earth's atmosphere and by any calibration uncertainties. For Eris, the reflectivity appears high compared with many other distant bodies, a property consistent with the surface that contains volatile ices that reflect sunlight efficiently. This property cannot be proven from brightness alone, but the brightness invites the hypothesis and motivates infrared and thermal observations later. At the discovery stage, the important point is that the object is large enough or reflective enough to stand out as unusually prominent among trans-Neptunian detections. The significance of such a discovery is also shaped by timing in the broader field. By the time Eris is recognized, the outer solar system is already known to contain many bodies beyond Neptune. Pluto is no longer alone. Surveys have found numerous trans-Neptunian objects of substantial size, though most are smaller than Pluto. The scientific community already understands that a population exists and that its members vary widely in orbit and composition. Yet the discovery of a particularly large and distant object still carries weight, because it tests the boundaries of that population. It suggests that the inventory may include multiple Pluto-scale worlds, and it implies that the solar system's outer region is richer in large bodies than older textbooks suggested. The act of discovery is therefore both specific and cumulative. It is specific in the sense that a particular dataset reveals a particular moving dot. It is cumulative because the dot gains meaning only within the expanding catalogue of known objects. When an object is recognized as unusually bright and distant, it enters the shortlist of large outer worlds. That shortlist has consequences, because size brings classification pressure. A large body can be spherical under its own gravity. It can hold on to certain ices more effectively. It can have a moon and a measurable mass. It can look, in basic physical terms, like a planet in miniature. The discovery data does not yet deliver all those properties, but it signals the possibility. The location of Eris in the sky at discovery also contributes to its importance. High-inclination objects can be found well away from the planetary plane. Such finds confirm that the outer solar system is not confined to a thin disk. They also confirm that survey strategies that focus narrowly on the ecliptic will miss part of the population. The discovery therefore adds to a broader methodological lesson. The outer solar system structure can only be mapped with wide coverage and repeated imaging. Each new high-inclination object strengthens that lesson and encourages more comprehensive surveys. The discovery data also carries a subtle lesson about human perception. In a single still frame, Eris is just a point. Its physical size, its distance, and its orbit are not visible in the pixel. They are inferred from motion and brightness. The transformation from point to world happens through repeated measurement and through model fitting. This is the normal path of astronomy, where physical reality is reconstructed from light and time. In the case of Eris, the reconstruction reveals not only a distant body but an object large enough to influence the language used for the solar system. At this stage, the story remains anchored in evidence and method. The data that first contains Eris is a set of survey images, repeated across time. The discovery emerges when motion is detected and confirmed. The object's unusual brightness and slow movement suggest a large or reflective body at great distance. Additional observations refine the orbit and allow earlier images to be recovered, extending the time baseline. The result is a clear orbital identity as a distant, high eccentricity, high inclination object of the outer frontier. From this point, the inward path moves toward precision. The next region focuses on orbit confirmation over time, showing how extended tracking reveals the full shape of Eris's path, its extreme distance range, and the slow scale of its year, turning a discovery dot into a well-defined member of the scattered outer populations. An orbit is not a single line drawn once. It is a solution refined by repeated observation. Each time Eris is measured against the background stars, its path becomes more defined. Early observations provide a short arc, a small segment of motion that can fit many possible trajectories. As the arc lengthens over weeks and months, many of those possibilities collapse. Over years, the orbit becomes firm enough to describe in clear terms a highly elongated path, strongly tilted relative to the planetary plane, with a year measured in centuries. This slow precision is the core of orbit confirmation, and it is the step that turns Eris from a promising discovery into a fixed element of the solar system map. Orbit fitting begins with positions on the sky at specific times. Each position is measured with reference to known stars whose coordinates are well catalogued. Modern surveys and follow-up telescopes use precise astrometry, the measurement of positions, to locate the object within the sky frame. The object's apparent motion is influenced by its own orbit and by Earth's orbit. When Earth moves, the viewing geometry shifts, and the object's apparent position changes accordingly. This parallax-like effect is useful because it contains distance information. A nearer object shows a larger apparent shift for the same change in viewing geometry. A very distant object shows a smaller shift. Therefore, the pattern of Eris's motion over an observing season provides constraints on distance and orbit shape. Initial orbit estimates often treat the object as belonging to a class of distant solar system bodies and use numerical methods to explore possible orbits consistent with the data. Because gravity from the Sun dominates, a two-body approximation provides the basic orbital framework, but precise fitting includes perturbations from planets, especially Neptune. Because the object's orbit intersects a region of space influenced by giant planet gravity over long time, the fitting process yields orbital elements, a set of parameters that define the orbit's size, shape, and orientation. Among these, the semi-major axis represents the orbit's scale, eccentricity represents how stretched it is, and inclination represents how tilted it is relative to a reference plane. As observations accumulate, the semi-major axis and eccentricity become more constrained. A highly eccentric orbit implies a large difference between the closest distance to the Sun, called perihelion, and the farthest distance, called aphelion. In such an orbit, the object spends most of its time far from the Sun because it moves more slowly when it is farther away. This is a general property of elliptical motion. The orbit confirmation process reveals this clearly for Eris. The object is discovered at a certain distance, but that distance is only one part of its long journey. The fitted orbit shows that Eris travels much closer to the Sun at perihelion than at aphelion. Yet it still remains far beyond the main planetary region, even at its closest approach. At its farthest, it reaches into a realm where the Sun's light is extremely weak. The inclination becomes clear as the orbit is refined as well. A high inclination means the object's path rises far above and below the planetary plane. This matters for dynamics because it suggests a strong past interaction history. It also matters for observation because it explains why Eris can be found far from the ecliptic. The orbit confirmation allows astronomers to predict where Eris will appear in future seasons and over long time, which is necessary both for continued study and for using the object as part of population statistics. The long orbital period follows from orbit size. Kepler's laws describe how orbital period increases with the size of the orbit. A large semi-major axis implies a long period. For a distant scattered disk object like Eris, The year becomes enormous compared with Earth's year. The orbit conformation therefore has a clear narrative consequence. The seasons on Eris, driven by changing distance from the Sun, unfold over centuries. This slow timescale affects everything else about the object's surface temperature cycles, volatile ice stability, and any possibility of a temporary atmosphere. Orbit conformation also benefits from recovery of pre-discovery images. Once an orbit is estimated, the predicted positions in past years can be computed. Astronomers can then search archival images for faint points at those positions. If Eris is found in earlier data, those measurements extend the time baseline dramatically. A longer baseline reduces uncertainty because it samples a larger segment of the orbit. It also helps resolve degeneracies, cases where different orbit shapes produce similar short-term motion. With pre-discovery detections, the orbit becomes not only more precise but more robust. The object's future positions become predictable with higher confidence, making it easier to schedule detailed observations. The orbit also places Eris within the broader dynamical categories described earlier. Its elongated and tilted path aligns with the scattered disk concept. Yet the exact classification can depend on the orbit's perihelion distance and on how strongly Neptune can currently perturb it. An object with perihelion close enough to Neptune's domain can be subject to ongoing scattering. An object with perihelion farther away can be more detached, influenced less by present-day close encounters. In practice, Eris's orbit is often treated as part of the scattered disk, and sometimes as part of a detached subset, reflecting the fact that its present orbit is stable and does not imply frequent close encounters with Neptune. The key point is that Eris occupies an extreme orbit within the outer population, demonstrating the range of solar system architectures beyond the classical belt. Orbit conformation also has a measurement consequence for physical size. The distance estimate derived from orbit fitting helps convert the object's observed brightness into an absolute magnitude, a measure of intrinsic brightness standardized to a reference distance. Absolute magnitude, combined with reflectivity assumptions, provides an initial size estimate. Without a reliable distance, that estimate is uncertain. With orbit conformation, distance becomes well constrained, and the size inference becomes more meaningful. The orbit is therefore not only a map of motion, it is a foundation for physical interpretation. There is also a subtle link between orbit and surface state. A highly eccentric orbit means large changes in sunlight over time. When Eris is far away, surface temperatures fall and volatiles tend to freeze. When it is closer, temperatures rise and volatiles may become more active. The orbit conformation therefore sets the context for later sections about seasonal effects and atmosphere. The object's climate cycle is written in its orbit parameters. At the end of orbit conformation, Eris becomes a stable coordinate in the solar system inventory. It has a defined orbit that can be predicted. It has a known distance range. It has a long period. It has a high inclination. These facts are not a matter of interpretation once enough observations exist. They are measured and fit. They set the stage for everything else. They also set the stage for the public narrative that follows, because a distant object that appears to be very large on a dramatic orbit invites a question of classification. Yet that question must wait. The inward path continues inward through the physical system of Eris itself. The next region focuses on the early designation and naming moment, including the temporary survey designation and the way early public discussion frames Eris as a possible new planet, before measurements and definitions settle into their final form. Before Eris has a mythological name, it exists in the records as a string of characters. That is the normal first identity of a new solar system object. Surveys and follow-up observations assign a provisional designation based on the year of discovery and the sequence in which the object's motion is recognized and reported. In this stage, the object is not yet a cultural symbol. It is a tracked point with a catalogue identity, an orbit that grows more certain with each observation, and a brightness that suggests unusual size or unusual reflectivity. The provisional designation is practical. It allows scientists to talk about the same object unambiguously while measurements continue. The provisional designation associated with Eris reflects that era of rapid outer solar system discovery. Surveys are finding many trans-Neptunian objects, and temporary names become a working language. The designation carries no claim about classification. It does not say planet or not planet. It does not say dwarf planet or not dwarf planet. It simply marks that a new moving body has been registered and that it can be followed again. In the quiet world of data, this is enough. The orbit can be refined, and the object can be placed into a dynamical category such as the scattered disk. Yet outside that data context, the appearance of a large new object beyond Neptune quickly becomes a different kind of event. Public attention gathers because the solar system is commonly taught as a finished list. For decades, Pluto holds a special place as the 9th planet in that list. Even after many Kuiper Belt objects are found, Pluto remains culturally unique. It is familiar, and it is tied to the idea that the solar system has 9 planets. When surveys begin to uncover other large bodies beyond Neptune, the scientific community adjusts steadily, but the public narrative moves more slowly. A new discovery that appears comparable to Pluto in size becomes an immediate stress test for that older narrative. It suggests that the list may not be complete, and that Pluto may not be alone. In this setting, early descriptions of Eris often emphasize its apparent importance in simple terms. The object appears large, it appears distant. Its brightness, once distance is known, implies either a large diameter or an unusually reflective surface. Early calculations place it near Pluto's scale, and in some analyses it appears to challenge Pluto directly. This comparison matters because it touches a long-standing category boundary. If Pluto is a planet, then an object at least as significant as Pluto seems to demand similar status. If Pluto is not unique, then the solar system may contain a class of Pluto-like worlds rather than a single outlier. At the same time, scientific caution remains necessary. Brightness does not equal diameter without a reflectivity estimate. Reflectivity, also called albedo, can vary widely among icy bodies. A smaller object with a bright surface can reflect as much light as a larger object with a darker surface. Therefore, early claims about Eris's size are provisional. They depend on assumptions that later measurements may revise. Yet even with that caution, the object's discovery at the time carries a clear signal. It is large enough to matter in classification debates, because it is not a small fragment. It is a world-sized body that is likely spherical under its own gravity and capable of holding volatile ices on its surface in the cold outer environment. The early phase also includes an informal naming culture that sometimes develops around provisional objects, especially when an object becomes a focus of public attention. Within the scientific process, the provisional designation remains the official label until a name is approved through established procedures. Yet in conversation, and in public reporting, an object that seems to be a new planet candidate can attract temporary nicknames and shorthand. These informal labels are not part of the final scientific record, but they reflect the social reality that discovery is watched as it happens. The naming process itself becomes part of the story, because names carry status in the public imagination. Formal naming follows conventions, A name must be proposed and then approved according to the rules of the relevant astronomical organizations. For objects in the outer solar system, names often come from mythological traditions. The name Eris eventually enters as a choice tied to the object's role in a classification dispute. Eris, in mythology, is associated with discord. The symbolism fits the moment because the discovery intensifies disagreement about what counts as a planet. Yet at the moment of discovery, before a final name is attached, the object's influence already exists. The influence comes from the orbit and the inferred physical scale, not from the label. This period is also characterized by a widening understanding inside the scientific community. The outer solar system is no longer described simply as Pluto plus empty space. It is described as a region filled with many bodies, some small and some large, organized into populations shaped by Neptune's gravity. Surveys reveal that large bodies can exist on different orbits, including resonant paths and scattered paths. In this view, Pluto becomes one member of a broader family rather than a singular planet at the edge. Eris enters as a particularly striking member of that family because it appears large and because its orbit is extreme. The discovery therefore sharpens an already developing scientific transition. The tension that follows is not a sudden invention, it is the result of competing needs. One need is descriptive clarity. A definition of planet should help organize knowledge and communicate structure. Another need is continuity with historical usage. Pluto has been called a planet for decades, and many people prefer that continuity. A third need is consistency. If Pluto is a planet, then similar bodies should also be planets, and that would expand the list dramatically as surveys continue. The discovery of Eris makes this consistency problem difficult to ignore. It brings the abstract question to a concrete example that cannot be easily dismissed as minor. The early public framing therefore often oscillates between two simple ideas. One idea is that a new planet has been found. The other idea is that Pluto's status is now questionable. The reality in the scientific process is more measured. The discovery adds evidence that the outer solar system contains multiple large worlds. It does not by itself dictate the final definition of planet, but it makes it harder to maintain a definition that includes Pluto while excluding other similar bodies. It also highlights the need for criteria that can be applied across the solar system in a consistent way. During this period, the object's moon becomes especially important, even before the wider public fully appreciates why. A satellite provides a way to measure mass through orbital motion. Mass is a fundamental physical property that can clarify comparisons. If Eris has a mass similar to Pluto's, then the comparison becomes stronger. If it differs, the comparison becomes more nuanced. The presence of a moon therefore moves the discussion from brightness and inferred size toward gravitational measurement. In the discovery narrative, this is the transition from suggestion to constraint. The object is no longer merely a bright dot. It becomes a system with a measurable mass. Even with the focus on classification, the deeper scientific value remains in what Eris represents about the outer solar system. A large scattered disk object implies that substantial bodies form and survive in that region, and that dynamical processes can place them on extreme orbits without destroying them. It implies that the inventory of a large trans-Neptunian objects is incomplete, and that more discoveries are likely as surveys improve. The public attention that gathers around a name and a category is therefore tied to a real expansion of knowledge about solar system architecture. In this region of the inward path, the story holds discovery before definition. Eris moves from a provisional designation in survey records to an object of public interest because it appears large and because it challenges a familiar list. The provisional label carries the discipline of data. The early public reaction carries the weight of cultural expectation. Between them sits the scientific process, which continues to refine orbit and physical properties, while the question of classification grows louder. The next inward step follows the system's physical measurement more closely. With a moon present, the mass of Eris can be determined through Dysnomia's orbital motion. That measurement becomes a firm anchor, more stable than early size estimates, and it sets the stage for understanding what Eris is as a physical world, rather than as a symbol in a definition debate. A distant object becomes easier to understand when it is not alone. A moon turns a single point of light into a measurable system, in the outer solar system, where bodies are faint and far away. This change is especially valuable. For Eris, the discovery of a satellite named Dysnomia provides that transformation. The moon is not merely an added feature, it is the key that allows gravity to be used as a ruler. With a moon, mass can be measured directly from orbital motion, and once mass is known, the physical meaning of Eris becomes sharper. Size estimates can still vary with reflectivity and thermal behavior, but mass becomes an anchor that does not depend on how bright the surface happens to be. A moon is detected in a different way than a planet-sized body. Eris itself is seen as a moving point against the star field, detected through repeated imaging and confirmed through orbit fitting. Dysnomia is far fainter and much closer to Eris in angular separation. Detecting it requires high-resolution observations and careful attention to glare and image structure. The light of Eris can overwhelm a nearby faint source, especially when the images are limited by atmospheric turbulence or by the optics of the instrument. A successful detection therefore depends on stable imaging and on methods that can separate a faint companion from the bright central source. Once Dysnomia is seen near Eris and confirmed through repeated observations, the meaning shifts. The moon's position relative to Eris changes with time, tracing an orbit. This orbit is not mapped in a single night. It is established through a sequence of measurements that show the moon returning to predictable positions. The pattern reveals that Dysnomia is bound to Eris by gravity, and that it follows a regular path around it. The orbit's period and scale can then be determined, and those values carry the mass information. The core concept is simple. An orbit is a balance between gravitational attraction and the inertia of motion. For a moon orbiting a primary body, the speed and period of the moon depend on the mass of the primary and on the distance of the orbit. When the orbit is measured, the mass can be inferred. This is a general method used throughout astronomy, from moons and planets to binary stars and galaxies. In the case of Eris and Dysnomia, the method is especially important because direct weighing is impossible, and because brightness alone cannot settle the question of how massive the object is. Brightness can suggest size, but it can mislead. An icy body with a very reflective surface can look brighter than a larger body with a darker surface. Thermal measurements can help by measuring the heat the object emits, which depends on size and temperature. But even thermal estimates can carry uncertainty when the object is very cold and distant. Mass measurement through a moon is different. It does not depend on surface reflectivity. It depends on orbital dynamics, which are governed by gravity and are stable over time. This is why the discovery of Dysnomia is often described as changing what can be said with confidence about Eris. The mass measurement also reshapes comparisons. During the initial discovery period, Eris is compared to Pluto because it appears similar in scale and because it occupies the same broad category of distant icy world. Yet Pluto's mass and size are known well enough to make a meaningful comparison only when Eris's mass is also constrained. Dysnomia provides that constraint. With a mass estimate, Eris can be compared more firmly to Pluto in terms of gravitational significance. This comparison matters for classification debates because the word planet, in everyday usage, often implies a certain scale and dominance. A large mass strengthens the case that Eris is a major body in its region, even if the region itself is different from the region of the 8 classical planets. The existence of a moon also tells a quiet story about formation and history. Moons of trans-Neptunian objects can form in different ways, including capture and impact. In the distant outer solar system, where relative speeds can be lower than in the inner solar system, capture can be possible under certain conditions, especially if a third body or dissipative process is involved. Impacts can also create moons by ejecting material into orbit. The exact origin of dysnomia is a subject of study and can be uncertain. But the presence of the moon indicates that Eris has had a dynamical history that includes close interactions. It suggests that the outer solar system is not only a place of quiet isolation, it is also a place where large bodies can collide or interact strongly enough to produce satellites. Dysnomia itself becomes part of the measurement chain in other ways. A moon can help constrain the system's center of mass, which is the point around which both bodies orbit. If the moon is relatively small compared with the primary, the center of mass lies inside the primary, and the primary's motion is subtle. If the moon is more substantial, the primary can show a small wobble. Measuring such wobble at the distance of Eris is challenging, but the concept remains important because it frames how mass is distributed and how accurately the mass can be inferred. In practice, most of the useful information comes from the moon's period and its orbital size as observed in the sky, combined with the distance to the system. Distance remains a supporting requirement. The moon's orbit is observed as an angular separation, a small angle on the sky. To convert that angle into a physical distance, the distance to Eris must be known. Orbit fitting provides that distance. Once the distance is set, the angular orbit becomes a real physical orbit, and the mass follows. This connection shows how different measurements combine astrometry for Eris's orbit around the Sun, imaging for dysnomia's orbit around Eris, and gravitational dynamics to turn those into mass. The mass measurement then influences the rest of Eris science. Mass combined with size yields density. Density suggests composition. A density higher than pure water ice implies a mixture of ice and rock, with rock contributing significant mass. A density closer to ice would suggest a more ice-dominated interior, because size estimates can vary somewhat. Density carries uncertainty as well, but mass provides a stable numerator in the calculation. This makes discussions of Eris's interior more grounded than they would be with size alone. The moon therefore helps move the story inward, from orbit and detection toward internal makeup. The moon also influences thinking about Eris's surface environment. In the outer solar system, satellites can experience different surface processing than their primaries. They can be smaller and thus less able to retain volatiles. They can have different reflectivity. They can also provide context for collisions and resurfacing, even when dysnomia itself is not studied in detail compared with Eris. Its existence contributes to the understanding of the system's history and stability. Naming follows discovery and measurement. The name dysnomia is attached after the moon's existence is confirmed, and the system becomes a recognized part of the solar system inventory. The names Eris and dysnomia are paired by mythological association, and in the scientific narrative they become paired by measurement. The moon's orbit becomes the means to weigh the primary. The act of naming does not change the physics, yet it marks that the system has moved from provisional status to established status, ready to be compared and discussed broadly. At this point in the inward path, Eris becomes a physical object with a measured gravitational scale. The orbit around the Sun establishes where it lives and how its seasons unfold. The Moon establishes its mass. With mass in hand, the story can proceed more confidently into the next layer of measurement, explaining how dysnomia's motion is analysed to yield that mass and why that result becomes one of the most secure facts about Eris. Mass is the property that turns Eris from a bright point into a gravitational world. It is also the property that's measured most cleanly once a moon is known. Dysnomia's orbit supplies the necessary clock and ruler. The clock is the orbital period, the time dysnomia takes to return to the same position relative to Eris. The ruler is the orbital size, the average distance between the moon and the primary. When these two are measured and combined with the system's distance from Earth, Eris's mass follows from orbital dynamics. This mass is not inferred from reflectivity or surface color. It is inferred from the way gravity shapes motion, and for that reason it becomes one of the firmest anchors in the entire story. The measurement begins with imaging. Dysnomia is faint, and it sits close to Eris in the sky. A telescope must resolve the pair as two separate points. This requires stable image quality and careful data reduction. The bright primary produces glare and diffraction patterns that can hide a faint companion. Observers therefore take multiple exposures, often using techniques that improve contrast between the primary and the region around it. Each successful detection yields a position for dysnomia relative to Eris, an angular separation, and an angle on the sky. One measurement is not enough. A sequence of measurements across time is needed to trace the orbit. As the measurements accumulate, the pattern becomes clear. Dysnomia does not drift away randomly. It remains bound to Eris and returns to similar configurations. Its relative position changes with a rhythm. This rhythm can be fit with an orbital model, producing an orbital period. The period is a direct observational result. It is the time between repeating positions, adjusted for the fact that the viewing geometry from Earth changes as both Eris and Earth move in their own orbits. The fit accounts for the slow motion of the entire system across the sky. In effect, the model separates dysnomia's motion around Eris from Eris's motion around the Sun. Orbital size is measured in a slightly different way. The images provide angular separations. An angular separation is not a physical distance until the distance to the system is known. Eris's distance comes from its orbit around the Sun, derived from many astrometric measurements. Once that distance is set, each angular separation can be converted into a physical separation in space. Over many observations, the set of separations traces an orbit that can be described by a semi-major axis. That semi-major axis is the characteristic size of the Moon's orbit. With period and semi-major axis in hand, the total mass of the system can be calculated using the standard relationship between orbital period, orbital size, and the gravitational constant. In practical terms, the relationship expresses that a more massive primary produces a faster orbit for a moon at a given distance, and a larger orbit produces a slower period for a given mass. This is a universal rule of gravitational motion for bound systems. In the Eris system, dysnomia's mass is small compared with Eris's, so the total mass is very close to the mass of Eris alone. The measured orbit therefore yields Eris's mass with only a small adjustment for the Moon's contribution. The strength of this method lies in what it does not depend on. It does not depend on how bright Eris is. It does not depend on whether the surface is covered in bright nitrogen frost or darker material. It does not depend on thermal models for emitted heat. It depends on geometry and time. The main uncertainties come from how precisely the orbit is measured and how accurately the system distance is known. Both can be refined with additional observations. Once the orbit is well sampled, the mass becomes stable across analyses, and the result can be compared directly to the masses of other outer solar system bodies. This mass measurement has immediate consequences for the debate that Eris eventually intensifies. Pluto has a known mass and a known moon system that provides gravitational information. If Eris's mass is similar to Pluto's, then the argument that Pluto is unique becomes weaker. If Eris's mass differs, the comparison still matters, but in a more nuanced way. The key point is that Eris is not a minor rock. Its mass places it firmly among the largest known trans-Neptunian worlds. It is a major body by gravity, and that gravity is measured rather than guessed. Mass also allows a more disciplined approach to size. A diameter estimate derived from brightness depends on reflectivity, and a diameter estimate derived from thermal emission depends on temperature and surface properties. Those diameter estimates can change as new measurements improve. Yet mass does not change in response to a new reflectivity model. Therefore, the relationship between mass and diameter becomes a check. If a diameter estimate combined with the measured mass implies an implausible density, then either the diameter estimate is wrong or assumptions about composition must be revised. In this way, mass constrains interpretation. It does not by itself provide a diameter, but it limits the range of diameters that make physical sense. The details of orbit fitting carry their own quiet complexity. The orbit can be inclined relative to the line of sight. It can appear as an ellipse in the sky, even if it is close to circular in space, simply because it is tilted. The measured positions must be fit with a model that accounts for this projection. The model yields not only the period and semi-major axis, but also the orientation of the orbit. Each parameter is adjusted until the predicted positions match the observed ones as closely as possible. The process is statistical and careful, and it improves with each additional measurement because additional measurements reduce the chance that an accidental fit is mistaken for the real orbit. There are also practical limits set by the observing geometry. Eris is visible at certain seasons when it's in the night sky. Dysnomia's orbit must be sampled across those seasons. Some orbital phases may be harder to measure if the Moon passes close to the primary in projection, where glare makes separation difficult. Therefore, the observational record can be uneven, and careful orbit fitting accounts for this by weighting measurements according to their uncertainty. The outcome remains the same in principle. Gravity sets the orbit. The data reveal the orbit yields mass. This mass measurement also clarifies a simple truth about the outer solar system. Many distant objects are discovered first through brightness, which can mislead because reflectivity varies. A moon removes that ambiguity. It provides dynamical information. This is why moons are so valuable in trans-Neptunian science. They turn unknowns into measured quantities. They provide mass, and mass provides gravitational context. In many cases, the presence of a moon is what transforms a newly discovered object from a catalogue entry into a well-characterized world. For Eris, the mass measurement also informs interior expectations. A body with this mass is large enough that internal heating from formation and from radioactive decay in rocky components can matter over long time. It is large enough to become spherical, because gravity can overcome material strength and reshape the body into hydrostatic equilibrium, a round form that reflects the balance of gravity and internal pressure. This roundness matters for classification in later sections, because one of the common physical traits of planet-like bodies is that they are rounded by their own gravity. Eris's mass supports this trait. It implies a world with enough gravity to shape itself and to hold on to certain volatiles when temperatures are low. The moon also hints at a history of interactions. A moon is often a sign that the primary has experienced an event that either captured a companion or created one through collision. In the outer solar system, both possibilities remain plausible, and the evidence needed to distinguish them can be limited. Yet the existence of dysnomia still supports the broader inference that the outer frontier includes active dynamical histories. Not only quiet, untouched debris, Eris is not merely a survivor. It is a participant in the complex gravitational life of the distant solar system. With mass established through dysnomia's motion, the story gains a firm backbone. Eris is not only large in appearance, it is large in gravity. The measurement is grounded in orbital dynamics and refined through repeated imaging and careful fitting. It becomes a stable reference for everything that follows. Size estimates can be refined, surface models can improve, atmosphere expectations can change with better temperature and albedo constraints. Yet mass remains one of the least ambiguous properties because it is tied to the motion of a moon, and motion is a direct expression of gravity. From this secure mass anchor, the inward path now moves toward the next layer of physical understanding. Mass alone does not reveal composition, but mass combined with diameter yields density, and density offers clues about what Eris is made of inside. The next region combines mass and size to infer density and to describe what that density suggests about rock, ice, and structure beneath the bright, cold surface. With mass anchored by dysnomia's orbit, Eris becomes a world that can be weighed, even at immense distance. The next step is to connect that mass to size. Size is harder because it depends on how much light the surface reflects and how much heat the body emits. Yet when a diameter estimate exists, even with uncertainty, mass and size together yield density. Density is the quiet bridge between what can be measured from far away and what can be inferred about the interior. A dense world suggests a significant fraction of rock mixed with ice. A less dense world suggests a more ice-dominated makeup. In the case of Eris, the evidence points toward a substantial mixture, consistent with a large body formed from the same outer solar system building blocks that mix frozen volatiles with rocky material. Diameter estimates begin with brightness. A bright object at great distance can be large, highly reflective, or both. Eris appears unusually bright for its distance, which immediately hints at a high reflectivity surface. Reflectivity, also called albedo, is the fraction of incoming sunlight reflected back into space. A high albedo makes an object look brighter without requiring a larger diameter. This is why brightness alone cannot fix size. A surface coated in fresh, pale frost can reflect strongly. A surface darkened by complex organic material can absorb more light and appear dim. In the outer solar system, where volatile ices can condense and where radiation can slowly alter surfaces, albedo can vary widely across objects of similar size. Thermal emission provides a second pathway. Any object with the temperature above absolute zero emits infrared radiation. The amount of emission depends on the object's temperature and surface area. For very cold bodies beyond Neptune, the thermal signal is faint, but it can still be measured with sensitive instruments. If the thermal emission is detected, it helps constrain the diameter because a larger object has more surface area and therefore can emit more total heat at a given temperature. Yet temperature itself depends on albedo, because a more reflective surface absorbs less sunlight and stays colder, while a darker surface absorbs more and warms slightly. Therefore, diameter and albedo are coupled, a thermal measurement, combined with reflected light brightness. can solve for both together in a model. The result is a diameter estimate and an albedo estimate with uncertainties that depend on the quality of the data and on assumptions about how the surface emits heat. Even with thermal data, interpretation requires care. A real surface is not a perfect emitter. Its thermal behavior depends on texture, grain size, and porosity. It depends on thermal inertia, a measure of how quickly a surface changes temperature when sunlight changes. A surface covered in loose frost can have low thermal inertia, warming and cooling quickly. A more compact surface can hold heat longer. Rotation spreads sunlight around the body, and if the rotation is rapid enough, day-night temperature contrast can be moderated. At the distances of Eris, the overall temperature is low, but these details still influence the thermal signature. Therefore, the diameter estimate is usually presented as a best value within a model framework, not as an exact geometric measurement. Once diameter is estimated, density follows from mass divided by volume. For a roughly spherical body, volume depends on the cube of radius. This introduces another source of sensitivity. A modest change in diameter produces a larger change in volume, because volume grows quickly with size. Therefore, density can shift meaningfully if the diameter estimate shifts. In contrast, the mass derived from dysnomia's orbit is relatively stable, so most density uncertainty comes from size uncertainty. This is a common pattern in trans-Neptunian science. Mass is anchored by dynamics, while size is refined by thermal and reflectance modelling. As size estimates improve, density becomes more precise, and interior inferences become steadier. Density is not a direct map of layers, but it is informative. Pure water ice has a lower density than typical silicate rock. A mixture of ice and rock will have a density between these end members, depending on the fraction of each, and on porosity, the fraction of volume that is empty space, in small bodies. Porosity can be high, because gravity is weak and cannot compress material tightly. In larger bodies like Eris, gravity is stronger, and deep porosity is reduced. Surface layers can still be porous, but the bulk interior is expected to be more compact. This means that bulk density in a large body more directly reflects composition than it does in a small rubble pile. Therefore, a density significantly above pure ice suggests that rock contributes substantially to the mass. In the outer solar system, a rock-ice mixture is expected from formation conditions. The protoplanetary disk contains both refractory materials, which remain solid at higher temperatures, and volatile materials, which condense only in colder regions. Beyond the region where water ice is stable, ice becomes a major solid component. Yet rocky material is still present because it forms the skeleton of planetesimals and provides the building blocks for cores. Large bodies that form in this region accrete both, producing a mixed composition. The exact rock fraction depends on local conditions, accretion history, and later evolution. But the mixed nature is a general expectation. Eris's density therefore fits the broader model of a large trans-Neptunian world, with a substantial rocky component and a thick mantle of ice. Density also hints at internal differentiation. Differentiation is the separation of materials by density, often with rock sinking inward and ice forming outer layers. Differentiation requires internal heating sufficient to allow materials to move and reorganize. A large body can have enough heating from two sources. One source is the heat of formation, generated when impacts and accretion release energy. Another source is the slow heat from radioactive decay in the rocky component. Over long time, this heating can warm the interior enough for partial melting of ice or for ductile flow. If differentiation occurs, The body can develop a rocky core and an icy mantle. The surface then reflects the chemistry and physics of the outer layers, while the interior carries the mass. For Eris, the evidence does not require a detailed interior map to suggest that differentiation is plausible. Its size and mass imply strong enough gravity and a history of accretion energetic enough to produce internal warmth. The presence of volatiles at the surface, indicated by spectral detections of ices in later studies, fits the idea of an ice-rich outer region. A differentiated interior would also influence the body's shape and gravitational field. Direct measurements of such fields at Eris are not available in the way they are for visited planets, so inference remains limited. Yet the density-based picture remains a reasonable framework, a large, mostly spherical world made of a mixture of rock and ice, likely with some internal layering. Another interior clue comes indirectly from the surface. A very bright surface implies fresh or clean volatile ice coatings. Volatile ices can migrate with temperature changes, freezing in cold seasons and sublimating in warmer ones. This migration can resurface the object, covering darker radiation-processed material with fresh frost. Resurfacing does not require internal volcanism. It can occur through seasonal condensation of volatiles from a thin atmosphere. If such processes operate on Eris, they keep the surface reflective and can also influence the near-surface composition. The interior does not need to be active in the way Earth is active. It only needs to be a reservoir of ice and rock that supports a surface layer where volatiles can move and settle. The moon system also enters the density discussion in a subtle way. A moon can provide clues about formation. If the moon formed from an impact, the primary could have experienced heating and mixing. Such an event could contribute to differentiation. If the moon formed through capture, the thermal history might be different. These possibilities remain uncertain without more detailed constraints on dysnomia's properties and orbit. Yet the presence of a moon still supports the broader point that Eris is part of a dynamical environment where large body interactions occur, and those interactions can influence internal evolution. Density does not settle the classification debate by itself, but it strengthens the physical picture that Eris is planet-like in some basic ways. It is large enough to be round. It has enough gravity to hold an orbiting moon. It is made of mixed materials like other planetary bodies. It is not a small fragment. These facts are part of why Eris intensifies the need for clear definitions later, because it resembles Pluto in physical character and belongs to a larger population of similar worlds beyond Neptune. The calm conclusion of this region is that Eris's measured mass and inferred diameter combine to indicate a substantial density consistent with a mixture of rock and ice. This density suggests a world with an interior that is likely compact and possibly layered, not a porous rubble pile. The uncertainties remain mostly in diameter and therefore in exact density, because albedo and thermal modelling determine size. Yet the broad inference is stable. Eris is a large trans-Neptunian world made from the same fundamental materials that build other outer solar system bodies, with enough gravity and mass to behave as a coherent, rounded body over billions of years. From this interior hint, the inward path now moves outward again in a controlled way, focusing not on deep structure but on the immediate surface that produces Eris's unusual brightness. The next region explores the reflective surface ices and the processes that keep that surface bright over long time in the cold outer sunlight. Eris stands out among distant worlds because it reflects a large fraction of the faint sunlight that reaches it. In the language of astronomy, it has a high albedo, meaning it is unusually bright for its size and distance. This brightness is not a superficial detail. It is a physical clue to the surface materials and to the slow processes that refresh or preserve those materials. In the cold outer solar system, certain volatile compounds can freeze onto the ground and form pale, reflective frosts. If those frosts remain clean, they keep the surface bright. If they are altered by radiation over a long time, they can darken. Eris appears to sit closer to the bright end of that balance, suggesting that volatile ices play a central role in its surface appearance. Light reflected from an object carries information about what it reflects off. Spectroscopy separates that light into a spectrum and reveals absorption features caused by specific molecules and ices. For distant icy worlds, the most commonly discussed surface volatiles include methane, nitrogen, and carbon monoxide, with water ice as a more refractory base material. Methane and nitrogen are volatile at relatively higher temperatures than water, meaning they're more likely to sublimate and recondense with changing sunlight. In the deep cold of Eris's orbit, these volatiles can freeze and remain stable for long periods. When they freeze as fine-grained frost, they can be highly reflective. A surface coated in such frost can therefore appear bright even when the body is far from the sun. Brightness alone does not prove which ice dominates, because both composition and texture matter. Grain size changes reflectivity. Fine grains scatter light efficiently and appear bright. Larger grains can appear darker because light penetrates deeper before scattering back. The presence of impurities also matters. Dark organic residues produced by radiation can mix with ice and reduce reflectivity. Therefore, the bright surface of Eris suggests not only that volatiles exist, but that the surface has been kept relatively clean or refreshed compared with darker trans-Neptunian objects. This is where slow seasonal cycles and volatile transport become important. Volatile transport is a quiet resurfacing process. When temperature rises even slightly, volatile ices can sublimate, turning from solid into gas. When temperature falls, the gas can freeze back onto the surface as frost. On a world with a highly elliptical orbit, the amount of sunlight changes substantially over a long year. Even though Eris remains far from the sun at all times compared with the inner planets, the difference between its closer and farthest distances still changes the surface energy balance. Over long times, this can drive cycles in which volatiles migrate, accumulating in colder regions and thinning in warmer ones. The effect is not a fast weather system. It is a slow redistribution of frost over centuries. If an atmosphere forms during the warmer part of the orbit, even a very thin one, it can serve as the transport medium. Gas molecules can move around the body and then condense where conditions favour freezing. This condensation can lay down fresh frost on top of older, darker material, increasing reflectivity. Even without a sustained global atmosphere, localized sublimation and recondensation can occur. In either case, the outcome is a surface that can be renewed. Fresh frost is bright. It masks older radiation-processed layers. Over long time, this can keep the surface reflective in spite of the constant bombardment of energetic particles and ultraviolet light that tends to darken exposed ice. Radiation processing is the opposing tendency. In the outer solar system, the surface is exposed to ultraviolet sunlight and to energetic particles from the solar wind and from the broader space environment. Over long time, these energies can break chemical bonds in surface molecules, producing new compounds. In methane-bearing ices, radiation can produce more complex hydrocarbons. Some of these products can be darker and redder than the original ice. The result on many distant objects is a reddened, darker surface layer, often described as an organic rich mantle. This kind of mantle can build up if the surface remains exposed and if there is no mechanism to cover it with fresh ice. Many Kuiper belt objects show this effect and appear dark and reddish. Eris's high reflectivity suggests that either this mantle is thin on its surface or that it is covered frequently enough by fresh frost that it does not dominate the reflected light. Temperature plays a key role in whether volatiles remain on the surface or escape. A small body with low gravity may lose volatile molecules over time because the molecules can reach escape speed more easily, especially during warmer periods. A larger body with higher gravity can retain volatiles more effectively, allowing long-term reservoirs of nitrogen and methane to remain. Eris's mass implies substantial gravity for a trans-Neptunian object, supporting retention. This helps explain why Eris can maintain a volatile-rich surface, while smaller objects may lose such ices or retain them only in sheltered regions. The bright surface also affects thermal behavior. A highly reflective surface absorbs less sunlight and therefore stays colder. This can create a feedback that supports volatile stability. If the surface is bright, it remains colder, which makes it easier for volatile ices to remain frozen. If it remains frozen, it can continue to be bright. This feedback does not guarantee permanent brightness, because radiation processing continues, and because temperature still changes with orbital distance. Yet it provides a stable tendency toward cold, reflective conditions when volatile frost coverage is high. The presence of a moon adds a subtle observational advantage as well. A well-characterized system encourages deeper study. When Eris becomes a focus of attention, because of its role in classification debates and because of its moon-based mass measurement, it receives more observational resources, more spectra are taken, more thermal data are gathered. As a result, the surface composition picture becomes clearer than it might for a less prominent object. This does not change the surface. It changes the clarity of the description. For Eris, that clarity supports the view that its surface includes volatile ices that help maintain its brightness. The surface state of Eris can also be compared calmly with Pluto. Pluto has a complex surface with multiple volatile ices and a known atmosphere that varies with season. Pluto's surface shows regions of bright frost and darker areas shaped by chemistry and topography. Eris appears, in broad terms, to be more uniformly bright at the resolution of distant observation, though the details of surface patterning remain uncertain without a close spacecraft visit. The difference can be influenced by current orbital position. If Eris is in a colder phase of its long orbit, volatiles may be more fully condensed on the surface, producing a broadly bright appearance. A future epoch closer to perihelion could produce different patterns as sublimation and atmosphere behavior change. This is not an imagined drama. It is a plausible consequence of volatile physics under changing sunlight. Even in cold regions, impacts occur. Small impacts can excavate darker material or expose fresh ice depending on depth and composition. Over long time, impacts can contribute to surface mixing, yet the dominant optical signature of Eris remains bright, suggesting that either impacts do not dominate the surface appearance or that any darkening they create is later covered by frost. The resurfacing power of volatile condensation can be strong in the outer solar system, because a thin global deposit of fresh frost can alter reflectivity significantly without requiring a thick layer. Uncertainty remains because direct imaging of Eris's surface at fine detail is not available. Observations integrate light across the disk. Spectra provide composition clues but average over the visible hemisphere. Thermal measurements constrain size and albedo but do not map small-scale variation. Therefore, the precise distribution of different ices on Eris remains uncertain. What is known is more general and still meaningful. Eris is exceptionally reflective compared with many similar distant objects. and that reflectivity is consistent with a surface strongly influenced by volatile ices and by resurfacing through condensation over long seasonal cycles. This bright surface sets the stage for the next inward layer, which follows from orbit rather than from composition. Eris's extreme orbital distance changes sunlight over a long year, driving temperature cycles that control whether volatiles remain frozen or become gas. The next region traces those slow seasonal changes, showing how orbit and temperature together shape the surface state and set the conditions for a thin, temporary atmosphere that may appear and disappear over centuries. Eris experiences seasons not through changing axial tilt in the familiar Earth sense, but through changing distance from the Sun along a highly elongated orbit. The change in distance alters the amount of sunlight that reaches the surface, and in the outer solar system even small differences in solar energy can matter for volatile ices. The cycle is slow. It unfolds over an orbital period measured in centuries. This slow motion creates a climate system that is less like a sequence of yearly events and more like a gradual shift in background conditions. Over long time, the surface alternates between relatively warmer states, where some ices can sublimate, and colder states where those same volatiles freeze solid and settle as frost. The amount of sunlight an object receives depends on its distance from the Sun. As distance increases, intensity falls with the square of the distance. A modest increase in distance produces a significant decrease in solar energy. In a circular orbit, distance remains roughly constant, and so does the average solar input. In Eris's elongated orbit, distance changes substantially. At perihelion, the object is closer and receives more sunlight. At aphelion, it is far and receives much less. Because Eris spends most of its time far away, its typical state is likely the colder one. The warmer state near perihelion is a smaller fraction of the long orbital cycle. Surface temperature depends on more than distance. It depends on albedo, because a reflective surface absorbs less energy. It depends on how efficiently the surface radiates heat away. It also depends on rotation, which spreads heating and cooling around the body. Yet distance remains the controlling variable over long time. A bright surface like Eris's reduces absorption, reinforcing cold conditions, but it does not remove the distance effect. When Eris is closer, it still receives more sunlight than when it is far. The surface temperature therefore rises and falls with the slow orbital rhythm. In the deep outer solar system, the relevant temperatures are low enough that common Earth gases behave very differently. Nitrogen, methane, and carbon monoxide can exist as ices. Their vapor pressures, a measure of how readily they evaporate into gas at a given temperature, are sensitive to temperature. A small temperature increase can raise vapor pressure significantly. This means that when Eris warms, even slightly in absolute terms, the tendency for certain ices to sublimate can increase. When it cools again, the tendency reverses and gases can freeze out. These physical properties create a natural seasonal cycle of sublimation and condensation tied to the orbit. If gas is produced by sublimation during a warmer phase, it can form a very thin atmosphere. The atmosphere would be tenuous compared with Earth's, and even compared with Pluto's at its more active phases. Yet it could still have real effects. Gas molecules can transport heat and can move volatile material across the surface. They can carry sublimated molecules from warmer regions to colder regions where they condense, depositing frost. This process can refresh the surface and maintain high albedo. When the season shifts toward colder conditions, the atmosphere can collapse as gases freeze back onto the surface, leaving vacuum above the frost. Even without a sustained global atmosphere, the seasonal temperature cycle can still move volatiles. Sublimation can occur locally where sunlight is strongest, or where surface properties allow more heating. Condensation can occur in permanently colder regions, such as areas that receive less sunlight due to local topography or due to the orientation of the rotational axis. The exact pattern depends on the object's tilt and surface geography, which are not fully mapped for Eris, yet the basic principle remains. Volatile molecules migrate from warmer to colder locations over time, driven by differences in vapor pressure and temperature. This migration tends to concentrate volatiles in cold traps and to lay down frost layers that alter reflectivity. The timescale of Eris's seasons matters because it is long enough that the surface can respond slowly and thoroughly. On Earth, seasonal changes are rapid compared with the thermal diffusion timescales of deep subsurface layers. On Eris, the long period means the surface can approach equilibrium with the long-term solar input at each phase more closely, especially in the upper layers. However, the surface is still subject to thermal inertia. Ice and rock can store heat and release it slowly. A very porous frost layer can have low thermal inertia and respond quickly. A more compact icy crust can respond more slowly. Therefore, the depth to which seasonal temperature waves penetrate can vary. The surface layer responds most strongly. Deeper layers respond with reduced amplitude and a lag in time. Over centuries, even deeper layers can change, but the change remains slow. The extreme distance range also implies extreme changes in sunlight angle and intensity across time. When Eris is far away, the sun appears smaller and dimmer. Shadows are deep, and the surface receives very little energy. In this state, volatiles are expected to be stable as ice, and any atmosphere is expected to be collapsed. When Eris moves closer, sunlight strengthens. In this warmer state, some volatiles can begin to sublimate. This transition may not be abrupt. It likely occurs gradually as the object approaches perihelion. The atmosphere, if it forms, may build slowly, becoming thicker as temperature rises. Then it may thin again as Eris recedes. Because the cycle is so long, the build and collapse can occur over many decades. The atmosphere's existence is therefore conditional. Observations indicate that Eris has a bright surface consistent with volatile frost, and that its orbital position implies long cold intervals. It remains uncertain how substantial any atmosphere becomes near perihelion, because Eris is not observed at all phases with equal detail, and because the relevant timescales are longer than the span of modern instrumentation. The physics, however, is clear. Volatile ices have temperature-dependent vapor pressures, and a body with sufficient gravity can hold a thin atmosphere when volatiles sublimate. A colder phase leads to freeze-out and atmospheric collapse. The seasonal cycle also affects what can be inferred about surface age and resurfacing. A surface covered repeatedly by condensed frost can appear young and bright because the frost masks older, darker, radiation-processed layers. This does not mean the underlying surface is young in geological time. It means the optical skin is renewed. In the cold outer solar system, a thin frost layer can persist for a long time because chemical reactions are slow. Yet radiation processing continues, and over time it would tend to darken exposed ice. Seasonal frost renewal counteracts that darkening. Therefore, the long orbital seasons support a plausible mechanism for Eris's high reflectivity. The interaction between orbit, temperature, and surface also links to the Moon system indirectly. A stable orbit and stable mass provide the basis for predicting future conditions. The orbit tells when Eris will approach perihelion relative to human time. The timescale is long, but it is predictable. Therefore, Eris can be treated as a world whose climate cycle is calculable. Observations made now capture it in one segment of that cycle. Future observations will capture it in another. Over long time, the cycle can be followed and the seasonal hypotheses tested. This is a distinctive feature of outer solar system science. The relevant seasonal periods can exceed human lifetimes, so understanding involves both observation and physics-based projection. In this region of the inward path, the orbit becomes the climate engine. Eris's elongated orbit produces long seasons through changing distance from the Sun. The temperature changes are small in absolute terms compared with Earth, but they matter because volatiles respond strongly at these low temperatures. The likely outcome is a surface state dominated by frozen volatiles for most of the orbit, with the possibility of a thin temporary atmosphere near perihelion and a collapse back to frost as Eris recedes. From this seasonal framework, the inward path moves to the atmosphere itself, treating it as a thin, temporary phase rather than as a permanent feature. The next region examines how such an atmosphere might form and freeze out, what it would be made of, and what remains uncertain in current observations. An atmosphere on a distant icy world is not always a permanent blanket. In the outer solar system, where temperatures hover near the freezing points of common volatiles, an atmosphere can behave like a reversible layer. It can appear when sunlight is strong enough to sublimate surface ices into gas, and it can disappear when cooling causes those gases to freeze back onto the ground. For Eris, this atmosphere is expected, if it exists at all, to be thin, seasonal, and tied closely to the long changes in sunlight along its orbit. Observations indicate that Eris has volatile ices on its surface and a very reflective appearance. It remains uncertain whether a substantial atmosphere is present at the orbital phase currently observed, and it remains uncertain how thick it becomes nearer to perihelion. The physical mechanism, however, is clear and steady. The key concept is vapor pressure. Each volatile ice has a characteristic tendency to become gas at a given temperature. At very low temperatures, vapor pressure is tiny, meaning the ice remains stable and little gas exists above it. As temperature rises, vapor pressure increases rapidly, meaning molecules leave the surface more readily. If enough molecules leave, they can form a thin atmosphere. Nitrogen is especially important in this context because it is abundant in the outer solar system as an ice, and because it can dominate an atmosphere when conditions permit. Methane and carbon monoxide can also contribute. The relative mix depends on the surface composition and on temperature, because each substance has different volatility. Gravity determines whether the atmosphere is retained. Gas molecules move with a distribution of speeds related to temperature. A body with higher gravity can retain molecules more effectively, because fewer molecules reach escape speed. Eris's mass and size imply a substantial surface gravity for a trans-Neptunian object. This supports retention of volatiles when they are frozen, and supports the ability to hold a thin atmosphere when they sublimate. Yet retention is not absolute. Over very long time, some molecules can escape, especially lighter ones, and the loss rate depends on temperature and solar input. The fact that Eris appears to retain volatile ices suggests that the loss has not exhausted its volatile inventory. Cold temperatures for most of the orbit further reduce loss, because colder gas moves more slowly and vapor pressure is lower. If an atmosphere forms, it interacts with the surface immediately. Gas molecules can move across the surface and condense where conditions are slightly colder. This can occur at higher latitudes if the rotational axis tilt creates polar cold regions, or it can occur in regions of higher albedo that stay colder, or in topographic depressions that receive less sunlight. Condensation deposits frost. Frost changes albedo. Albedo changes temperature. This feedback can create patterns of bright and less bright terrain over time. For Eris, the integrated brightness suggests broad frost coverage, but the fine pattern remains uncertain without detailed imaging. Even without mapping, the physics supports that atmospheric transport, if present, can redistribute volatiles and renew the surface. Atmospheric collapse occurs when temperature falls enough that vapor pressure drops and gas condenses. The collapse is not a dramatic storm, it is a slow settling. Gas molecules strike the surface and stick, building frost layers. The atmosphere thins. Eventually, the remaining gas becomes so tenuous that it no longer behaves like a continuous fluid. It becomes a near vacuum with occasional molecules. In this state, the surface is effectively exposed to space again. The presence of a frozen volatile layer is then a record that an atmosphere once existed or could exist under warmer conditions. The collapse therefore connects the atmosphere to the surface frost in a natural cycle. The orbital timescale makes this cycle long. Eris's perihelion and aphelion are separated by centuries of travel. If an atmosphere grows near perihelion, it may persist for decades in a gradually changing form, then slowly collapse as the object recedes. The exact timing depends on thermal inertia, on albedo, and on the thickness and composition of surface ices. Thick nitrogen ice can buffer temperature through latent heat, the energy absorbed or released during phase changes. As nitrogen sublimates, it absorbs energy, limiting temperature rise. As it condenses, it releases energy, limiting temperature fall. This buffering can moderate the cycle and influence how quickly an atmosphere grows or collapses. The presence of methane can also affect this because methane can be less volatile than nitrogen under the same conditions and can remain as a surface component when nitrogen is migrating. Spectral observations provide hints about what is on the surface and therefore what an atmosphere could contain. Absorption features consistent with methane ice indicate that methane is present. Methane can also exist as a trace gas in a nitrogen atmosphere, as on Pluto, and it can influence the atmosphere's thermal balance because methane absorbs infrared radiation. Whether Eris's atmosphere, if present, behaves in a similar way remains uncertain, because the atmosphere may be too thin to observe directly at present distance and phase. The presence of methane ice still supports that methane is available for exchange between surface and atmosphere under appropriate conditions. Direct detection of an atmosphere at Eris is difficult. At such distance, even a substantial thin atmosphere would produce subtle signals. One method used for distant bodies is stellar occultation, where the body passes in front of a background star and the star's light is measured if the body has an atmosphere. The starlight can fade gradually rather than sharply as the atmosphere refracts and absorbs it. The shape of the light curve can reveal atmospheric pressure and structure. Such events are rare and require precise predictions and coordinated observations. When observations exist, they provide constraints on whether an atmosphere is present and how dense it is. For Eris, current constraints indicate that any atmosphere at the time of certain observations is very thin or absent, consistent with a cold phase where volatiles are largely frozen. This fits the seasonal framework. It does not rule out a thicker atmosphere near perihelion in the distant future. The possibility of an atmosphere also has implications for surface freshness. An atmosphere that collapses deposits frost. Frost covers older layers. The result is a bright surface. This matches Eris's high reflectivity. The cycle can occur even if the atmosphere is present only intermittently and at low pressure. A small amount of gas can still transport frost over time, especially across a long season. Therefore, Eris's brightness can be consistent with a world that is currently cold and airless, yet has experienced atmospheric phases in the past, and will likely experience them again as it approaches perihelion. Eris's atmosphere, if it forms, is expected to be extremely cold and thin, with molecules moving slowly in a low-scale height compared with warmer atmospheres. The atmosphere's composition would likely be dominated by nitrogen if nitrogen is abundant at the surface, with methane as a minor component, and possibly carbon monoxide in trace amounts. The exact mix depends on surface ice ratios and temperature. The atmosphere would be sensitive to sunlight, to albedo patterns, and to local temperature differences. It would also interact with the surface by depositing and removing frost, creating a slow chemical and physical exchange between solid and gas. This region completes the transition from orbit-driven climate to surface-driven appearance. A thin, temporary atmosphere is the natural intermediary between sunlight changes and frost deposition. It provides a mechanism for resurfacing and for maintaining high albedo. It also provides a link to the broader scientific interest in Eris as a Pluto-like world. Pluto has a known atmosphere and active volatile transport. Eris appears to share the materials and the physics, though in a different orbital phase and likely with a different atmospheric behavior at present. With atmosphere described as a reversible layer, the inward path now turns toward the human classification pressure that makes Eris historically important. The physical story has established that Eris is a large, round, massive, volatile-rich world in the outer solar system, similar in character to Pluto and other large trans-Neptunian bodies. The next region shows how this similarity forces a question about what a planet is, and why Eris becomes the discovery that changes the definition. The solar system's categories feel stable when the inventory is small. For much of the 20th century, the map taught in schools contains 9 planets and a scattering of smaller bodies. Pluto sits at the edge as an odd member, distant and small, yet still part of the planet list by historical convention. Over time, discoveries beyond Neptune reshape that picture. The Kuiper belt becomes known as a population of many icy bodies. Some are large enough to be rounded by their own gravity. Pluto begins to look less like a lone planet and more like one prominent member of a broader class. In this evolving context, Eris arrives not as an abstract challenge but as a concrete example. It is large, massive, and distant, and it follows an extreme orbit. Its discovery intensifies a classification pressure that is already building and makes it difficult to keep the old list without rewriting the meaning of the word planet. The pressure begins with similarity. Eris is not a comet nucleus with a fleeting tail and a small nucleus. It is not a small asteroid. It is a world-sized body, large enough that gravity shapes it into a round form. It has a moon, which allows its mass to be measured. Its surface shows volatile ices that behave in ways familiar from other outer solar system worlds. These physical traits resemble Pluto's traits more than they resemble the traits of minor debris. The resemblance matters because the term planet in common use implies a class of major worlds, not a single historical exception. The pressure also comes from quantity. Once surveys begin to find multiple large trans-Neptunian objects, the idea that Pluto is uniquely deserving of planet status becomes harder to defend on physical grounds alone. If Pluto is a planet because it is round and orbits the Sun, then Eris satisfies those same traits. If Pluto is a planet because it is a large body beyond Neptune, then Eris is also a large body beyond Neptune. If Pluto is a planet because it is culturally familiar, then the definition becomes historical rather than scientific. The discovery of Eris forces a choice between these approaches. It does not create the problem, but it makes the problem visible and immediate. The outer solar system context strengthens that visibility. The region beyond Neptune is not empty space. It is a reservoir of objects with a range of sizes and orbits. Pluto is part of that reservoir. Eris is part of that reservoir as well, though in a more extreme orbital category. The presence of multiple substantial bodies means that any definition that calls Pluto a planet based on physical similarity would likely expand the planet count. As surveys continue, additional Pluto-sized or near Pluto-sized bodies are found. A definition that includes all of them would eventually produce a long and growing list of planets. Such a list might be acceptable as a cultural choice, but it weakens the communicative value of the category as a way to describe the solar system's main architecture. The architecture of the solar system contains clear dynamical structure. The 8 classical planets dominate their orbital zones. Each of these planets either captures or ejects smaller bodies in nearby space over long time, shaping the local distribution of debris. Each sits in a region where its gravity is the primary organizing force. Pluto does not fit this pattern. Pluto shares its region with many other Kuiper belt objects. Its orbit is stabilized by resonance with Neptune, and it is one of many bodies in a belt-like population. Eris, though massive among distant bodies, also does not dominate its entire region in the way the 8 planets do. It is one large body among a broader set of distant populations shaped by Neptune's gravity and by the solar system's early dynamical history. The classification pressure therefore points toward including dynamical dominance as a distinguishing trait. The discovery of Eris also influences the public narrative because it arrives at a moment when the Pluto question is already active. Scientists have been discussing the Kuiper belt as a population and Pluto as part of it. In that view, calling Pluto a planet becomes a choice that is not forced by physics. Eris provides a strong example that makes the choice unavoidable. If Pluto remains a planet, then Eris appears to demand the same label in many people's minds, because the physical differences are not large enough to justify separate categories under a simple size-based rule. If Eris is not labelled a planet, then Pluto's label is questioned. This is the hinge point. Eris turns a gradual shift in understanding into an immediate need for definitional clarity. Within the scientific community, the debate is not simply about pride in an object. It is about building a classification that helps describe the solar system in a coherent way. Categories are tools. They are meant to group objects that share meaningful traits and to separate objects that differ in important ways. A planet category can be defined by physical shape and orbital status alone, which would include many bodies as discoveries continue, or it can be defined by dynamical role, emphasizing whether the body dominates its orbital neighborhood, or it can be defined by formation history. Though formation history is harder to infer directly for many objects, each approach has consequences for how the solar system is taught and understood. Eris intensifies the debate because it is close to Pluto in the most visible ways. It is a distant icy world with planetary scale traits. Its mass and size make it hard to dismiss as a minor body. Its orbit makes it a member of a large outer population rather than a solitary outlier. Therefore, it forces the question of whether planet should be a broad term for all round bodies orbiting the Sun, or a narrower term for bodies that are gravitationally dominant in their orbital zones. The debate that follows is partly about language, but language here encodes a scientific picture. The narrow definition aligns with the view of a solar system structured by 8 dominant planets and additional populations of smaller worlds and debris. The broad definition aligns with the view of many planets, including multiple trans-Neptunian worlds, which reflects a different emphasis. The debate is also shaped by the word dwarf planet, a term that emerges as a possible compromise. The term suggests that an object can be planet-like in shape and composition, but still belong to a population of similar bodies and not dominate its orbital zone. In this conceptual space, Pluto and Eris can be treated together as large round worlds in the outer populations, while the 8 planets remain the dominant bodies in their regions. The term does not reduce the physical reality of Pluto or Eris. It places them into a category that acknowledges both their planet-like nature and their context within a belt and scattered populations. Eris plays a specific historical role in driving this outcome. Its discovery demonstrates that Pluto is not unique, and it demonstrates that the old planet list is not merely missing small fragments. It is missing other substantial worlds. This makes it difficult to justify Pluto's planet status as a singular exception. It also makes it difficult to expand the planet category indefinitely without losing the category's usefulness as a guide to the solar system's structure. Therefore, Eris becomes the discovery that makes the existing tension resolve into an official definition process. The classification crisis also has a quiet philosophical dimension. Scientific definitions often follow discovery rather than precede it. In many fields, categories are refined when new examples blur old boundaries. The outer solar system provides exactly such an example set. Pluto is discovered before the Kuiper belt is recognized. Pluto is named a planet when the outer population is unknown. Later, when many similar bodies are found, the category must be reconsidered. Eris is one of the most influential of these later finds because it is large, and because it arrives at the right moment in the growth of data. It acts as the lever that moves the conversation from informal debate to formal criteria. This region of the story therefore holds 2 truths together. Eris does not change physical reality in the outer solar system. It reveals physical reality more clearly, showing that there are multiple large, round worlds beyond Neptune. At the same time, Eris changes the language used to describe that reality by making a historical category inconsistent with the expanded inventory. The discovery forces clarity because the category must either expand greatly or become more precise. The pressure is not emotional in the scientific sense. It is logical. It is the pressure of applying the same rule to similar objects. With this classification pressure established, the inward path now moves to the formal decision itself. The next region describes the planet definition adopted in 2006 and explains how the criteria apply to Eris and Pluto, including the requirement that separates major planets from dwarf planets in the official framework. The formal shift in the definition of a planet occurs when a scientific community chooses a set of criteria that can be applied consistently. In 2006, the International Astronomical Union adopts a definition intended to clarify how to describe the growing inventory of solar system bodies. The decision does not change orbits or surfaces. It changes the classification language used to describe them. In this framework, a planet is not simply a round body orbiting the Sun. It is a round body that also plays a dominant dynamical role in its orbital region. The definition introduces a separate category, dwarf planet, for round bodies that share their orbital neighborhoods with many other objects. Eris is one of the central examples that makes this distinction meaningful. The definition rests on 3 criteria. The first is that the object orbits the Sun. This criterion separates planets from moons, which orbit planets rather than the Sun directly. It also frames the definition as specific to the solar system, rather than as a universal rule for exoplanets, which are not under the International Astronomical Union's direct naming and classification system in the same way. In this solar system context, Eris satisfies the first criterion because it orbits the Sun directly on a long, elongated and tilted path beyond Neptune. The second criterion is that the object has sufficient mass for its self-gravity to overcome rigid body forces so that it assumes a nearly round shape. This is sometimes described as hydrostatic equilibrium, a condition in which gravity pulls inward and internal pressure pushes outward until the body settles into a stable, rounded form. In practical terms, this criterion distinguishes large bodies that become spherical from smaller bodies that remain irregular because their material strength can resist reshaping. Eris satisfies this criterion. Its size and mass indicate that gravity is strong enough to produce a rounded body, and its measured mass from Dysnomia's orbit supports that it is large and coherent rather than a loose aggregate of fragments. The third criterion is the one that becomes decisive for Eris and for Pluto. It states that a planet has cleared the neighbourhood around its orbit. Clearing the neighbourhood does not mean the orbit is empty in an absolute sense. It means the object is gravitationally dominant in its orbital zone. Over the age of the solar system, it has removed other comparably sized bodies from nearby orbits through gravitational scattering, accretion, or ejection, leaving itself as the primary mass in its region. This criterion is dynamical rather than purely physical. It treats a planet as an architect of local orbital space, not merely as a rounded object. The orbit-clearing idea aligns closely with the observed structure of the 8 classical planets. Each one is far more massive than the total mass of other objects that share its orbital zone. Each has either absorbed smaller bodies, captured them as moons, or scattered them into different regions. Earth shares space with asteroids, but none of those asteroids approach Earth's mass. Jupiter shares space with Trojan asteroids and other small bodies, but Jupiter dominates the region by gravity. In this view, a planet's neighbourhood may contain debris, but it does not contain multiple bodies of comparable scale sharing the same orbital band. Pluto does not meet this third criterion. Pluto resides in a region filled with many Kuiper belt objects. Its orbit is stabilized by resonance with Neptune rather than by its own dominance. The total mass in Pluto's orbital neighbourhood is not negligible compared with Pluto's mass, and Pluto is one among a population rather than the primary mass of a cleared zone. Eris also does not meet the orbit-clearing criterion. Even though Eris is massive among trans-Neptunian objects, it resides within a broader population of distant bodies whose orbits reflect the same dynamical history. Its orbit is extreme and tilted, but it is not the gravitational ruler of a cleared region in the way Neptune is in its zone, or Jupiter is in its zone. Eris is a major member of a population, not the sole dominant occupant of an orbital lane. The International Astronomical Union definition therefore places Eris and Pluto into the dwarf planet category. A dwarf planet, under this framework, orbits the Sun and is round, but has not cleared its orbital neighbourhood and is not a moon. This category acknowledges that objects like Eris and Pluto are planet-like in physical form and complexity. They are not small rubble. They can have differentiated interiors, volatile cycles, and moons. The difference is their dynamical context. They share their region with many other bodies, and therefore do not define the solar system's primary architecture in the same way. In the real science view, the orbit-clearing criterion is best understood as a spectrum rather than as a poetic phrase. Clearing depends on mass, orbital distance, and the history of gravitational encounters. A large mass helps clear because stronger gravity can scatter or accrete other bodies more efficiently. Distance matters because orbital periods are longer and encounter rates differ in the outer solar system. Over billions of years, the 8 planets become clearly dominant in their neighbourhoods. In the Kuiper belt and scattered disk, the situation is different. The populations persist. Neptune's gravity shapes their distribution, and the region remains a reservoir of many bodies. A single object like Pluto or Eris does not remove the population, because the population is large and because Neptune's influence is the dominant sculptor of the entire region's dynamics. Therefore, the orbit clearing criterion separates bodies that dominate their zones from bodies that are embedded within larger reservoirs. This is where Eris's discovery becomes pivotal in hindsight. Without Eris, Pluto might still appear singular enough that a purely historical classification could persist with less friction. With Eris, the presence of at least one additional body comparable in scale to Pluto makes inconsistency harder to ignore. The definition provides a consistent rule. If Pluto were a planet under a simple roundness rule, Eris would also be a planet, and then other large trans-Neptunian objects would follow as discoveries continue. The International Astronomical Union chooses the dynamical approach to keep the planet category aligned with the major gravitational architects of the solar system, while still recognizing that round bodies beyond Neptune are real worlds deserving their own category. The dwarf planet category also expands beyond Eris and Pluto. It includes other large bodies in the Kuiper belt, such as Haumea and Makemake, and it can include Ceres in the asteroid belt, because Ceres is round and orbits the Sun but does not clear its neighbourhood. This is an important feature of the definition. It unifies the idea that roundness occurs at multiple distances and in multiple populations, and that roundness alone is not used to define the primary planet list. The solar system becomes a structure with a small set of dominant planets and a larger set of dwarf planets and smaller bodies in belts and scattered populations. Uncertainty and disagreement remain part of the story, but they are not the same as confusion about the criteria. Some disagreement focuses on whether orbit clearing is the best dividing line for teaching and public understanding. Some disagreement focuses on the process and wording of the definition itself. Yet the scientific meaning of the adopted criteria is clear. Under this framework, Eris and Pluto are both dwarf planets because they orbit the Sun, are round, and do not dominate their orbital neighbourhoods. The definition therefore treats them together, matching the physical similarity that Eris's discovery makes harder to ignore. The decision also changes the way the outer solar system is narrated. The region beyond Neptune is no longer framed as a lonely planet followed by emptiness. It is framed as a population of worlds and debris, with a few large members and many smaller ones. Pluto becomes a representative example rather than an exception. Eris becomes another representative example, particularly of the scattered and detached populations. The category change does not diminish their interest. It places their interest in the context of a richer frontier. It also encourages attention to dynamical families and to the processes that shape them, such as planetary migration and resonance capture. In this steady framing, the International Astronomical Union definition becomes the hinge between discovery and language. Discovery reveals that the outer solar system contains multiple large bodies. Language adapts by distinguishing between physical planet-like traits and dynamical dominance. The new categories provide a map that can grow as surveys continue, allowing new objects to be placed consistently without rewriting the planet count each time a Pluto-sized world is found. With the formal definition now set and applied, the inward path is ready for the final synthesis. The next region describes what Eris changes in a lasting way beyond the headlines, a clearer inventory of outer worlds, a stronger focus on populations and dynamics, and a calmer, more precise way to speak about what a planet is in the modern solar system. Eris changes the definition of a planet not by demanding attention through spectacle, but by arriving as a clean, physical example that exposes a boundary in the old language. It is large enough to be round, massive enough to hold a moon, and cold enough to host volatile ices that behave like the materials on Pluto. Its orbit places it in the outer frontier populations shaped by Neptune's gravity, and by the solar system's early migration history. These traits make it difficult to treat Pluto as uniquely deserving of planet status, without also granting that status to a growing family of similar worlds. The discovery therefore accelerates the transition from a historically inherited planet list to a definition designed to remain consistent as the inventory expands. The lasting change begins with the inventory itself. Before the modern era of wide-field surveys, the region beyond Neptune is often summarized in public understanding as Pluto and little else. As surveys map the Kuiper belt and scattered disk, the outer solar system becomes a populated frontier. Eris is one of the most important of these finds because it is among the largest, and because its physical scale is comparable to Pluto's. It demonstrates that Pluto is part of a class, not a solitary exception. This shift in perspective has a calm, scientific value. It encourages the outer solar system to be studied as a set of populations with distributions of size, orbit, and composition, rather than as an appendix to the planet list. The discovery also strengthens the role of method. Eris is found through repeated imaging and careful motion detection. Its orbit is refined through long tracking and archival recovery. Its mass is anchored through dysnomia's orbital motion. Its surface properties are inferred through spectroscopy and thermal modeling. Each step depends on measurement and on model discipline. The story becomes a demonstration of how distant worlds are studied without spacecraft, using light and gravity as tools. This is part of what changes after Eris. The public narrative becomes more aware, at least within scientific communication, that the solar system is still being discovered and that its categories are built from ongoing evidence rather than from a fixed list. The classification change itself is a tool for coherence. By separating the ideas of roundness and dynamical dominance, the International Astronomical Union definition allows the solar system to be described with a stable planet category that highlights the major gravitational architects, while still recognizing that round, planet-like bodies exist in multiple belts and reservoirs. Eris fits the dwarf planet category in this framework. The term does not imply smallness in a trivial sense. It implies a different dynamical role. Eris is a major world embedded within a population rather than a solitary dominant body in a cleared zone. This distinction becomes more important as more objects are found, because it allows a consistent placement of new discoveries without constant redefinition of the main planet list. The consequences extend into how the outer solar system is taught and imagined. The solar system becomes a layered system. The inner planets and the asteroid belt form one region. The giant planets and their systems form another. Beyond Neptune, belts and scattered populations form a third region with its own internal categories. In this view, Eris is not an outsider. It is a representative of the scattered frontier, a world that shows that planet-like bodies exist beyond the classical planets, and that these bodies come in families shaped by dynamical history. The focus shifts from the idea of a ninth planet to the idea of a population of trans-Neptunian worlds. Eris also contributes to a calmer understanding of what planet-like means physically. A round body with volatiles and a moon can have complex processes even at great distance. Seasonal cycles can occur on timescales of centuries. Atmospheres can appear and collapse through freeze-out. Surfaces can be resurfaced by frost deposition. Density can imply differentiated interiors of rock and ice. These are the qualities that make Eris scientifically interesting regardless of category. The dwarf planet label does not remove them. It places them into a context where similar processes are expected across multiple bodies in the Kuiper belt and scattered disk. The discovery also highlights how definitions respond to discovery. Scientific categories are not imposed from outside nature. They are negotiated tools that change when new data reveal that old boundaries are too crude. Pluto's original planet status is assigned before the Kuiper belt is known. Eris arrives after the Kuiper belt is recognized as a population, and its physical similarity to Pluto makes the old category boundary unstable. The response is a definition that incorporates dynamical context. This is a pattern across science. A new example forces a refinement in language, and the refined language then guides future classification in a way that reduces confusion as more examples appear. Another lasting change is the emphasis on orbital neighborhood as a meaningful organizing idea. The 8 planets are not only large and round, they dominate their zones. They shape the distribution of smaller bodies in their vicinity. This dynamical dominance is a strong descriptor of architecture. Eris and Pluto do not exhibit the same dominance. They are embedded in populations shaped primarily by Neptune's gravity and by the collective history of migration and resonance. Recognizing this difference helps explain why the outer solar system remains a reservoir rather than a set of cleared lanes. It also helps explain why discovering more Pluto-like objects is expected rather than surprising. The definition thus encodes a realistic picture of how the solar system is arranged. The continuing uncertainty is not about whether Eris exists or what category it falls into under the adopted definition. The continuing uncertainty lies in details of surface composition, the exact behavior of seasonal volatile transport, the extent and timing of any atmosphere, and the history of the Moon's formation. These uncertainties are natural for distant objects that have not been visited by spacecraft. They represent active edges of study rather than gaps in basic understanding. The basic truths remain clear. Eris is a large trans-Neptunian world. It has a moon. Its mass is measured. Its orbit is extreme. Its surface is bright and volatile rich. These facts are enough to support the historical role it plays in classification. In the calm end, the story of Eris is a story of the solar system becoming larger in concept without becoming more chaotic in understanding. The inventory expands, and the language adapts. The planet list becomes a description of dominance and architecture. The dwarf planet category becomes a description of round worlds embedded in belts and scattered populations. Eris sits as a steady example that bridges these ideas: a world that is physically planet-like, dynamically part of a population, and historically important because it makes the boundaries of old language visible.